When drawing resonance forms, you want to remember that you only exchange the position of pi bonds and the non-bonding electrons. Remember, a pi bond would be the second bond in a double bond, or the second and third bonds in a triple bond. Sigma bonds are never moved. Also, you never want to exceed an octet for second row elements, so don't give carbon more than 4 bonds. There are 5 general bonding patterns that, if you learn to recognize them, can help you predict when resonance will occur. The first would be the allylic lone pair. The second is the allylic carbocation. The third is having a lone pair of electrons adjacent to a carbocation. The fourth is a pi bond between 2 atoms with differing electronegativities. And the last would be conjugated pi bonds in a ring. And the only way to recognize these patterns is to do lots and lots of practice problems. So let's define some terms. The vinyl position refers to the actual carbon of the double bond. The allylic position or allyl position refers to carbons adjacent to a double bond. So we want to look for lone pairs on an allylic atom. It doesn't have to be a carbon. So here we have a lone pair on the nitrogen, and that lone pair is on the nitrogen which is adjacent to a double bond. And over here, that is not allylic because that nitrogen is not adjacent to a double bond. All of the lone pairs drawn here in these examples are allylic. So you have a lone pair and it's on a carbon adjacent to a double bond. Here, both lone pairs on the oxygen are on an atom adjacent to a double bond. Here, the lone pairs in this oxygen are on an atom, the oxygen atom, next door to a double bond. So it doesn't have to be a carbon-carbon double bond, it could be a carbon-oxygen double bond. Similarly, you have a lone pair here next door to this carbon-nitrogen double bond. And this is an amide functional group. Here you have a lone pair on this nitrogen, and that lone pair is on an atom next door to a double bond. When you show the resonance structure for this pattern, you actually will use 2 curved arrows to show the movement of the allylic lone pair. And this illustrates the arrows. So you're going to have one arrow going from the lone pair to the center of the bond between the carbon with the lone pair, or the atom with the lone pair, and the next door atom. And then simultaneously, you're going to have a second curved arrow showing movement of the pi bond, and you're going to draw it from the center of the pi bond to the atom there. So here we have the arrow going from the lone pair to the center of the bond between the atom with the lone pair and the atom connected to a double bond. And then we show the 2 electrons on the pi bond moving to that atom. And you can look through the rest of these examples. When an atom with an allylic lone pair has a negative charge, the charge is also moved with the lone pair. So notice here what's different. The placement of this double bond has changed, as has the placement of the lone pair, as has the placement of the negative charge. In this example, the lone pair here becomes this double bond, and the pi bond here becomes the second lone pair. And if you were to do a formal charge analysis using the equation, you would see that that negative charge is now going to belong to the nitrogen, not the carbon. If the allylic atom is neutral, then it will become positive, and the atom receiving the lone pair will become negative. So here we've got a lone pair becoming this pi bond, and that pi bond becoming this lone pair. And in doing so, you've now put a formal plus charge on the oxygen and a negative charge on the carbon. If you're not sure what the charges will be, you can always do a formal charge analysis. And then in this next example, we have the lone pair on this nitrogen becoming this pi bond, and this pi bond here becomes a third lone pair on the oxygen, and in doing so you've now created formal charges, a plus charge on the nitrogen and a minus charge on the oxygen. The second pattern is a little bit easier. It is the pattern of the allylic carbocation. A carbocation is simply a carbon with a positive charge. So in this, you're just going to use one arrow to show the movement of the electrons, and the pi bond here changes places and moves over here. And notice the positive charge also moves to the other carbon. If there are multiple double bonds that are separated only by single bonds, they are what we call conjugated, and you can actually get multiple resonance structures. So the way you would do this is draw one resonance structure at a time. So here's your allylic carbocation. So first you're going to move this double bond over, and when it does that, the positive charge also moves, and then you just do it a second time. So move that double bond over again, and then you get to this third resonance structure. That means that there is now a total of 3 resonance structures for this allylic carbocation. The third pattern is having a lone pair adjacent to a carbocation. So here we have a lone pair on an atom directly next door to a positively charged carbon. So that lone pair is going to become a double bond with the adjacent carbon, and in doing so, that positive charge moves to the oxygen. So it's important to recognize how, along with the movement of lone pairs and pi bonds, formal charges are also affected. And if you're not sure what the formal charges are going to be, always you can go through the formal charge analysis using the equation that we've talked about. The fourth pattern is probably the simplest. It's when you have a double bond or a pi bond between atoms that have different electronegativity. The most common thing we'll see in here is a C double bond oxygen. And in this, to draw the resonance, you just simply are going to move the 2 electrons in this pi bond up onto the oxygen atom to create a third lone pair. And in doing so, you end up with a negative formal charge on the oxygen and a positive formal charge on the carbon. These 2 structures represent the extreme descriptions of the pi bonded electrons, and the actual compound is a hybrid of the 2. The final pattern would be conjugated pi bonds in a ring. So conjugated means you have pi bonds that are interrupted by a single bond, so it's alternating double bond, or it could be double bond, single bond, triple bond, pi bonds alternating with single bonds. So in this, all of the pi bonds will move, shown here, so they all are just moving over one place to get to the other resonance structure. And again, it's not that these 2 resonance structures are going back and forth, it's that the actual structure is a mixture of these 2. This is a summary of the 5 main patterns and the types of arrows that we use in showing the movement of electrons to get to the next resonance structure. Now here's an example. So if we have this allylic carbocation, this fits one of our 5 bonding patterns. So we have a carbon with a plus charge adjacent to a double bond. So here the pi bond is simply going to move over towards the positive charge. So it's going to move to be between these 2 carbons. And when that happens, that positive charge has to also move to the other carbon. If you're not sure what happened to the charges, you can always do a formal charge analysis. Now try drawing a resonance structure for this molecule. So this fits the bonding pattern where you have a double bond between carbon and a more electronegative atom. And here we're simply going to take the pi bond and move it to be a lone pair on the oxygen. Now I didn't draw in the lone pairs that already exist on oxygen, so I'm going to go ahead and do that now. There's 2 lone pairs. And then I'm going to draw my double-headed arrow, which is the special arrow we use when we're drawing resonance structures. And then I now have 3 lone pairs on the oxygen, a single bond between the carbon and the oxygen, but I also have to put in my formal charges. If you're not sure what they would be, you should do your formal charge equation. Now let's try this example. So here we have a lone pair adjacent to a double bond. So this would be the pattern of an allylic lone pair. So here the lone pair from the nitrogen is going to form a double bond with the adjacent carbon, and then the pi bond is going to break and end up as a lone pair on the carbon. I'm going to draw my special double-headed arrow. And here I have now my new structure. So notice I have the new pi bond between nitrogen and its adjacent carbon, and then I broke the other pi bond and formed this lone pair. But I also have to indicate what my formal charges are. I now have a negative charge on that carbon, and the nitrogen is now neutral. Now we're going to move along to acids and bases. So in the Bronsted-Lowry definition of acids and bases, acids are molecules that contribute a lot of H pluses, and bases are molecules that can accept H pluses. So it's really focusing on the transfer of H pluses between two molecules. So acids give up a proton or H plus, and bases accept a proton. And acidity is the measure of the tendency of a compound to lose a proton, whereas basicity is a measure of a compound's affinity for a proton. So here is your general acid-base reaction. So we often will write HA as our general abbreviation for an acid, and B with a lone pair is our general abbreviation for a base. And in this reaction, the base is going to grab the H from the acid, and when the acid loses its proton, it forms what's called a conjugate base. And when the base accepts its proton, it forms what's called a conjugate acid. Here is a specific example. So HCl, hydrochloric acid, is the acid. Here water is acting as the base. So water is going to grab the proton from HCl to form this conjugate acid, and Cl- is the conjugate base. Here we have another example. So in this case, water is the acid, and NH3 is the base. So NH3 is going to grab that proton to form this conjugate acid, and then the acid, after it gives up its proton, forms this conjugate base. So the conjugate base is the product that results from deprotonation of the acid, and the conjugate acid is the product that results from protonation of the base. So let's try that with this reaction. Let's label the acid, the base, and the conjugate acid and conjugate base. Since I've given you the reactants and the products, you can just look and see what happened. So notice that here water, this H moved over to this oxygen. So the water gave up its H, so it must be the acid. And this other compound grabbed the H, it accepted the proton, so this must be the base. And then when the base accepted the proton, it formed what we call the conjugate acid. And when the water, which was acting as the acid, lost its proton, it formed what we call the conjugate base. So you have the acid and base on the left-hand side in the reactants, and the conjugates on the right-hand side. We used curved arrows in organic reactions to show the making and breaking of bonds. We also used them to show the movement of electrons in drawing resonance structures. So when we have an acid-base reaction, the base is going to grab the proton with a lone pair. And we illustrate that by drawing a double-headed arrow originating at the lone pair and ending at the hydrogen atom. And then the hydrogen's going to leave, but it's not taking any electrons with it. So it's going to leave behind both electrons in the bond it had to the remaining part of the molecule. So the two electrons in that bond are going to stay behind as a lone pair on the rest of the molecule. So here's a specific acid-base example. So here we show the base attacking the acid. So we draw a double-headed arrow from the lone pair on the base to the hydrogen of the acid. And then that OH bond breaks, and we show an arrow from the center of that bond and ending at the oxygen atom. So the 2 electrons in that bond then become a third lone pair on that oxygen atom. So this is the base, this is the acid. When this grabs the proton, it forms the conjugate acid. When this loses its proton, it forms its conjugate base. Now see if you can predict the products and draw arrows and label the conjugates. So pause the video and see if you can do this, and I've helped you out by telling you which compound is the acid and which compound's the base in both reactions. And notice that water in the top reaction is acting as a base, and the bottom reaction it's acting as an acid. This just shows that compounds can act either as the acid or the base depending on what they're paired with. So here is the answer. So if water is the base, it's going to be accepting the hydrogen. And to draw the arrows, we draw a curved arrow originating at the lone pair on the base and ending at the hydrogen atom. Then we have to show that the hydrogen leaves and the bond breaks between it and the atom it was bonded to. So we draw an arrow from the center of that to the oxygen, creating a third pair on that oxygen. So when water accepts a proton, it forms this conjugate acid, and when acetic acid loses its proton, it forms the conjugate base. We also can use terms called electrophile and nucleophile, which we'll discuss later in the semester. Nucleophile just means nucleus loving. It's another name for a compound that likes to react with something that is electron deficient. An electrophile is electron loving, so it's something that loves electrons like lone pairs of electrons. In the next example, we show an arrow from the lone pair on the base to the hydrogen atom, and then again we're breaking the bond between the hydrogen atom and the atom it was bonded to. And then when this grabs the proton, it forms its conjugate acid, and when water loses its proton, it forms the conjugate base. Another key concept is the acid dissociation constant, Ka. So we could take any acid, dissolve it in water according to this equation, where when we dissolve it in water, we form H3O plus and A minus. So in this case, this is acting as the acid, giving up its proton, and water is acting as the base. And you can write an equilibrium constant for any reaction, which is just simply the concentration of the products over the reactants. Now notice that we don't have water listed in the Ka expression. That's because water is a pure liquid, and our rule from general chemistry is that we ignore those in equilibrium constant expressions. The numerical value of Ka is used to predict the extent of acid dissociation. So if the product concentrations are very great, that means that that reaction proceeds far to the right, and that would mean that this dissociates readily. So a large Ka value indicates a strong acid, whereas the reverse is also true. A small Ka value indicates a weaker acid. In other words, if you have a strong acid, the HA will give a lot of H3O plus, but if you have a weak acid, it's not going to dissociate much. It's going to kind of hang out like it is as HA. Now we often use what are called pKa values because they're easier to work with than the Ka values, and they are just the negative log of the Ka. And I'll show you a table of pKa values. Stronger acids have smaller pKa values. Weaker acids have larger pKa values. Here's a table of some representative pKa values. So here ethanol has a pKa value of 16. HCl, hydrochloric acid, has a pKa value of -7. So ethanol with the pKa of 16 is a much weaker acid compared to HCl with a pKa value of -7. And just think about the fact that you drink ethanol, that's just alcohol, but you would definitely not want to drink hydrochloric acid. Here's an example. Consider the amino acid phenylalanine. It has a pKa of 1.83. Let's compare that with tryptophan, which has a pKa of 2.83. Which is the stronger acid? So the answer is that phenylalanine is the stronger acid because it has the smaller pKa.